You're on.
Good afternoon, good evening, wherever you happen to be in the world. My name is Steve Bryant, and I'm happy to be here as part of the CNPS annual conference. And I want to do a brief introduction because I don't think I've had a chance to meet everyone in the room yet. My name is Steve, and I've been part of what was formerly NPA and now this organization since, I want to say around 2000, so somewhere in that time frame. Have not attended every conference, but have done my best to attend many of them. And over the past couple of years, I've kind of been in hiding. As David mentioned, I was busy working on a book called Disruptive, Rewriting the Rules of Physics, and we're going to be talking about that a little bit today. In terms of my background, by education, I have a computer science undergraduate degree, so that's kind of my technology and math foundation. And I have a MBA, which is where I did, I'll call it communications, relationship, and strategy. And you'll see that blended in the conversation that we're going to have this evening. But my role today isn't one of those. Today, I'd like to play a role of messenger. And in that role, we're going to talk about things that many of you already know. And that's really the power of what we'll talk about. It's not so much, oh, this is Steve's idea or Steve's theory or something like that. Really, we're going to be reinforcing things that you've learned throughout your educational and professional careers, some of them as young as grade school. So that's the power, and that's the excitement. I'm going to start with a number, and the number is 30,700,000. Anyone venture to guess what that number means? 30,700,000. No guesses?
Big?
I'm sorry?
Big?
Big, yes, it is big. And it's actually a search I did the other night, and it's the answer as a Google search to the question, or to the statement, Einstein is wrong. And when it comes back, it says there's 30 million entries. so there's a lot out there, which means that there's a lot of dialogue out there about theories like Einstein's theory of relativity, both pro or con, right? People are just engaged in that type of discussion. And we heard, for those of you who were here earlier today, I think David did an excellent job kicking off our purpose and framing why we were here. But we heard 5 specific points from David, maybe 6. I'm just gonna write down what I had captured earlier. And these are things that you hear about the dissident community. Number 1 was it's pseudoscience, so not real science. Number 2 is that nothing good will come from the NPA. I think that was a quote. Number 3, people don't understand modern science. Number 4, we need to show that we understand mainstream physics. And the last one that I have here is that we are salesmen with no buyers. And I thought that was all very, very interesting because all of those create barriers, right? These are all real barriers in terms of how effective we are in getting, whether it's an individual message out there or a group message out there. In fact, one of the things I want to do, if my iPhone works properly, we'll see if the magic of technology actually works and how well my undergraduate degree in computer science plays in here. But I want to play something for you. It's really short, and it's just going to reinforce what David mentioned. And it was an interview that Neil deGrasse Tyson did, and I just want to play the question and then hear his answer, because this is, in effect, what we have to respond to.
Is from Hugh. Hugh wants to know, could I please ask Dr. Tyson when and if Einstein's theory of relativity will be fully discredited?
It will never be discredited because it works. So I have theories. You have to understand.
I love that segment. At some point in the future, I look forward to actually meeting him and having a discussion about that statement. But that is the reality, right? There's a lot of people out there who believe that it will never be discredited because it works. Okay? Now, what's interesting is with that type of statement, there's actually power in that statement that you can use to actually prove it wrong. And that's what we'll talk about today, because what we have to do is not necessarily agree that it's right, but we do have to show why it gives useful answers. And if we can do that, as well as 2 other steps, then we can empower ourselves or the organization, whether it's in my message or a group message or your message or any message that we'd like to communicate. So really, this is about strategy, and it's about an approach. And in this case, the approach is 3 words, and they're around the principle KISS. I'm only going to do one of the S's though. So keep it simple. If you've heard that phrase before, you know what that is. So really, one of the principles is keeping it simple. And one of the things that we're going to do is talk about a principle that is 3 elements. The first is a statement of the problem. The second is an alternative that ideally works better. And third is you have to answer why. So why does it work better? Why do people believe the original approach, etc. And we actually have an advantage because we know what the mainstream positions are. There's not 100 of them. There's not 1,000 of them. There's basically one with a few offshoots. And so we know what that is, and it empowers us to figure out strategically how do we want to have a conversation around relativity, in particular, how would we go about challenging it. So I'm going to hand out some pieces of paper. This is group activity, by the way. It is part of the, before the quiz.
I got it for you.
Okay, cool, thank you. Okay, so if we can pass those out, and while we're passing those out, I'll just explain what you're looking at here. This is an idea, and what I tried to do on this page is convey the amount of different ideas that we have as a community. I'm not saying that they're good, I'm not saying that they're bad. I am saying we have a lot of different ideas out there. And one of the things I'd like you to do with me now is just take that page and hold it up in front of you. Okay, good, most people are holding that up. And rip it, just rip it. Rip it in half. It doesn't matter, vertical or horizontal, just go ahead and rip it in half. Okay, I did that for a reason because I wanted to convey a concept. And the concept is when we're unfocused, when we have a lot of ideas, when we ourselves aren't on the same message, even if or core message, we don't have to agree on everything, but if there's foundational things we can't agree on, our voice won't carry. We won't affect change in a broader sense, maybe on individuals, but not as a group. And it really does make it hard or easy for people to come in and rip what we're doing. So the ideas that David mentioned earlier in terms of how people are critical, what you just heard from Dr. Tyson, those are real because one side is focused, the other one we have a lot of ideas. So we're going to pass out some more. And as we're passing those out, I'm going to ask you to go on a journey with me for a moment. And on this journey, you can keep your eyes open because I know it's late, so I'm not going to ask you to close your eyes to go on this journey. But on this journey, I'd like you to imagine tomorrow. Imagine what does that look like in terms of ideas, thought leadership, scientific transformation, theories that people in this group would stand behind and say, that sounds rational to me, right? So if that's what a tomorrow looks like, well, how can we do that? And what might we do different? Well, one idea is, and you heard Bruce mention it today, is we can start to get aligned around some of our terminology and ideas like that. You also heard David talking around critical thinking and starting to align around those principles. So what I'm going to ask you to do is apply the power of focus to the page that I just handed you. So if you can take that page and fold it once in half. Doesn't matter vertical or horizontal. I learned, Bob. And let's fold it again. Let's fold it twice. Okay, because each time we're getting it more and more focused. Let's do it a third time. fact, I'm going to ask you to do it 4 times because we're going to come back to the number 4 in a moment. And for those who are really industrious, if that's the right word, go ahead and fold it a 5th time. Okay, what we've taken is ideas and we've concentrated around key ideas or messages or thoughts or concepts that we can rally behind as a community and then start to build upon, which I think gives us power, it gives us unity, it gives us focus. Try and rip that page in half without unfolding, right? For most of you, it's very challenging. I think we have a winner. Which is why I'm glad I said for most. But for most of us, it's very, very challenging to rip that because of what I'm using in this example is the concentration or the focus. Can it be ripped? Absolutely. Will it? Time will tell. But one thing that this demonstrates is if we are united and if we're focused around different concepts and ideas, then that gives us power, both in terms of what we do, but it also positions us to have dialogues and conversations with the mainstream. And I'll come back to that in a moment. I'm going to save this, and we're making good progress here. So now we're going to talk a little bit about relativity. I mean, what would it be for a guy who's been known in the NPA community as talking about relativity for the past years and get up here and not talk about relativity. So we're going to talk about that, but we're going to do it in a different way. We're not going to talk about all of relativity. We're just going to talk about specific parts of it, and we're not going to talk about it directly, and there's a reason for that, which we'll get to in a moment. But before we do that, I want to share a story. And it's a story from about 7 years ago, and I was helping my daughter with some math. So at the time she was about 8, and she was almost in tears because she couldn't do this math problem. And I was trying to help her through it, and as we were walking through it together, I just said, Sarah, this is no different than English, right? So what we have to do here is you have to learn, you had to learn your basic math before you can do this, and just like you had to learn your ABCs before you could learn how to read, and now you can read anything. And without missing a beat, she turns to me and goes, no, I can't read your mind. So now I share that because that answer was unexpected, right? And it's a valid answer, but it was completely unexpected. And what I hope to share in the next, let's say, half an hour or so, maybe a little less, is something that's a little bit unexpected. And we're going to talk now a little bit about Einstein and his paper. And we're going to first begin by asking a question. And the question is, and I was thinking about this at dinner, is it a when or is it a where? And I put when and I have where on that piece of paper, so I'm not sure what is the right word to begin with. But I'm going to go with where. So where does relativity begin? Right? Where does relativity begin? And if you're looking at the paper, then if you're looking at his paper, then you could say, well, it begins with his 1905 paper on the electrodynamics of moving systems and blah, 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 but where? When do we move from not having relativity theory to having relativity theory, right? And it happens in a place that I refer to as his spherical wave proof. And the spherical wave proof consists only of 6 sentences. And I'll read 3 of them to you tonight. But those 6 sentences, the first one and the last 2, are probably the 3, I'll call it most overlooked sentences in terms of what I'll talk about. But I think they're probably 3 of the most important for us as a community to understand what the implications are. So it reads, and I'm reading an English translation because I don't speak fluent German. So it begins, we now have to prove that each ray of light reproduces itself as measured in the moving system with a velocity of c, if that is what we assume is the case in the resting system. For we have not yet supplied the proof that the principle of the constancy of the speed of light is compatible with the principle of relativity. Okay, this is really important, because what he's saying at that point, he's already done some math in sections 1, 2, this is about halfway, maybe a little bit more in section 3. He's already done all of that, and now he makes a statement that says, we do not yet have relativity. Okay? That's really important, because until we get to this next phrase, relativity doesn't exist. He has a few other sentences in there, which we'll talk about in a little bit more detail, that have a couple of equations. Then he says, coming out of those equations, so the transform wave, when viewed from the moving system, is a spherical wave that propagates at velocity c. This proves that both principles are compatible, period. I argue that that is the instant that relativity comes into existence. Okay? Because he said up front, he's done some math, but he hasn't shown that his ideas are compatible. So he can't use anything relativistic up at that point. He does some other stuff, which is his spherical wave proof, and then he comes out of it and says, because I've shown that the transform shape is a spherical wave, I can now say my two principles are compatible, the proof is done, poof, relativity exists. Now that's really an important point, and it's super important. I keep walking around, I don't want to trip myself here. It's a really important point, because before that period, there is no relativity, which means two things. I can't argue against relativity theory using any relativistic concepts or ideas, but the power is any attack on relativity that happens prior to that point cannot be defended using any relativistic terms or ideas. Remember, you can't use prior knowledge in a proof, so anything like simultaneity, time dilation, length contraction, all those ideas happen after the period, not before. So let's just pass these around. I'd like everyone to just, play with them. They're nerves. Don't throw it too hard. So,
Is the football properly inflated?
okay, so as those are making their way around, good. As they're making their way around, we're going to ask a question. What does it take to be spherical? So, I asked my daughter, I love bringing my daughter into this. She's actually one of my sounding boards. I believe if I could explain something to her using age-appropriate concepts, that I'm probably making sense of the world. So, I don't necessarily need to use partial differential equations or some other concepts that I might use if I'm talking to someone else, but at least it gives me an opportunity to say, okay, does this make sense to you? What do you think is a rational idea? Is that getting bigger or smaller? And if she can give the appropriate answer, I'm like, okay, I'm on the right path here. So I asked her to describe a circle, and she was able to do that. I asked her to describe a sphere, and she was able to do that. And if you look at these, there's two of them going around. One's orange and white. If I was to ask different people, what's the difference between a spherical shape and an ellipsoidal shape? What might you say are some of the differences? If you want to talk in math terms, feel free, but I'm just looking for English. How do you describe the difference to somebody between those two shapes?
The sphere, no matter how you hold it, it feels the same.
Okay, so sphere is kind of the same everywhere.
It feels the same.
Okay. Anyone else on
And no matter which way you turn it, its shadow always projects a circle.
Oh, for a sphere, right. Whichever way you turn it, its shadow will always project a circle, so it's straight on shadow. Okay. Anyone else?
Volume per surface area is different.
Okay, volume to surface area is different. Okay, so these are all good, and what that says, right, is that there's a lot of different ways that we can use, a lot of different words that we can use to describe a sphere, or similarly an ellipsoid, or those types of shapes. In mathematics, we have an equation for those, right? And so what I'd like to do here is we're going to pass out a few more things here. So David, if I can get your help on that.
Absolutely.
I don't know how many are in this stack, but if we can make sure everyone gets one, that'd be great.
I played poker, so.
Okay, so this is my cheat sheet card, and we're only going to look at the front of it for right now. We'll go to the back in a bit. On the front, what I've done is remember we've read of Einstein's 6 sentences that make up his spherical wave proof. We've read 3 of those sentences. Okay, I'm not going to read all the other 3, but I will say that there's 2 equations that appear in those other 3 sentences. The first equation is on the top, and the second equation is on the bottom. And what's unique about those equations is that if you look at them and you read them very, very quickly, you're going to say, yep, both of those are what we learned early on in our academic careers. These are equations for spheres. And since the equality is maintained in both equations, we quickly conclude that we have 2 spheres, an original sphere and a transform shaped sphere. And because that equality is always maintained, we come out of that statement and we go into Einstein's conclusion, which I read earlier, which is why everyone believes that the spherical wave proof has passed. But, and this is a very important but, if you actually do the work and you plot some points, so you take a sphere and you take all the points, and then you know, this is the power of Excel and computers, which Einstein didn't have the advantage of. You put it into a computer, and then you say, okay, transform all those points. What you get out is something that satisfies that second equation with an important notation. And you see that in bold, the radius for each of those transform points changes. So yes, we do have equality maintained, but you don't have a spherical surface, because a spherical surface requires the radius to be constant, which means that the spherical wave proof has failed. Why is that important? Because you can see the arrow. If you have a sphere, I only draw it in 2D though, so the sphere goes to a circle. Rest assured, no, it doesn't. But I'm much better at drawing 2D than 3D. So the top one, because the constant radius, it will always be a spherical surface. That's true. The bottom one, because r changes with each point, remember Einstein gives you variables on the right side of the equation and on the left side of the equation. So he maintains his equality, but because he's giving values on both sides, you cannot state what the shape is. And so it could be a squiggle. It could be a collection of random points. As long as when he passes that collection of random points, x, y, and z, and he's also passing t, which is multiplied by c, that's how he gets r. So x, y, z, and r will always maintain that equality. So that's pretty powerful, I think, because what it does is it neutralizes the conversation around paradoxes or assumptions or time dilation or all these other things that we have to argue if relativity is right. And here's the important thing, we haven't proved relativity was wrong. So I didn't come up with a new theory that says, okay, this new theory displaces relativity. All we've done is we've said, let's apply what we already know, the rules of mathematics, and what we're going to show is that Einstein needed another step in his proof, right? So if you only do the 5 steps he shows in his proof, you'll reach the exact same conclusion that he did, that we all have done for the past century. The last step is you have to confirm that the radius is not changing. And once you do that step, you'll find, oops, the radius is changing, therefore you do not have a spherical wave, therefore the proof fails. Once we show the proof fails, this is an invitation now, right? Because people are going to go, it's failed, but what's the alternative? And it seems to work. Both of those we have to have a response to. Okay, and because our leadership, for us as a community, for us as individuals, to help transform the wider, the broader academic and scientific community, we have to acknowledge where things like relativity, where it works, where it doesn't work, if it doesn't work, why it doesn't work, etc. So what we're going to do here is what I'm calling a little bit of scientific martial arts, which is we're going to take the energy that they have when they say, yeah, but Steve, thank you for this proof, but relativity, it works. It gives us good answers. Okay, we have to address that. And we have a strategy for that. That's where we come with an alternative. And David, I still need your help. Okay. Pass these out. Hopefully we have enough. If not, let me know.
You got one? Okay. Don't expect free stuff from us tomorrow.
You're supposed to rip this in half?
I think I should have thought about laminating them beforehand because the lady over here kind of ripped it, so I think we need to do that. Okay, before I go to the back of this, which is where we'll start to talk about an alternative, I do want to talk about the front a little bit, because one of the things I feel is I hope is powerful when we start talking about things that we might be able to unite around as a community. It doesn't mean we have to unite around everything. You might not like everything that I'm saying, but if there's certain foundational things that we can put in place that we can say, okay, this is our foundation. We may all have different first stories, second stories, third stories, but let's, if we can say this is our foundation, maybe we start to build momentum around that. On the front of this page is a no math story around what I just walked through. So it says, if you look at the top, Einstein started with a spherical wave. And what's important is you have that circular shape that we talked about. The center and the origin are the same. And if you draw lengths from the center to any point, all those lengths will be the same. That's not the case in the transformed shape. It's ellipsoidal. The center and the origin are no longer coincident. The chord lengths do not come from the center, nor do they come from one of the foci. They come from the origin. And the lengths aren't the same. You can draw the picture. This happens with any velocity greater than 0, although it's more visibly visible with greater velocities. And this is a simple visualization that we don't have a spherical wave. So now that we've shown that, well, what's the alternative? Now, if you turn it over, you'll see a model that I introduced in my book called modern mechanics. In modern mechanics, you can think of it as building on the best of geometric transformations and explaining what it is Einstein was trying to do. Okay. So let's talk about that a little bit. So you'll see in the middle, you'll see some things. So what's different? First, let's talk about what's the same. You still have this concept of an outer system. What I call an outer system, Einstein calls a stationary system. Similar, not exact, similar. I have an inner system. Einstein calls it a moving system. Again, similar enough that we can, if you wanted to think about them as the same, it's close enough that you can say, okay, they're similar ideas. Then there's this other idea of an oscillating system. Now, what's surprising is Einstein actually has an oscillating system in his paper. and it's called the ray of light. And he has equations in the math go back and forth. And we'll talk about that in a moment. What we do is we explicitly say, okay, well, that's another moving system. Now, here's the thing about moving systems. There's a couple of things you can explain. They're not all explained by the same equation, right? So one thing that you can explain is, where are you? I was here, now I'm here. That's a positional change. Positional changes are in the terminology of mathematics, they're called translations. For those of you who are in physics, you think of Newtonian transformations, things of that nature. So you just move from one point to another, there's equations that govern that. There's another type of equation, which you can imagine if you have a rubber band. I should have brought rubber bands. But if you have a rubber band and you stretch that rubber band, right, that stretching motion is called scaling, and that's a different type of transformation, different set of equations. In a system with a lot of moving things, you might have multiple things going on. You might have things moving because of translation. You might have things moving because of scaling. You might have rotation. There's a whole host of geometric transformations out there. We're only talking about 2 of them this evening. And to talk about 2 of them, I'm going to ask you to help me with an example here. And this is one, again, it's already been test-driven on my daughter and her friends as the test subjects. So I'm going to ask you to imagine that there's a bus waiting right here on this main street out in front of the hotel. And this bus is 14 meters long, so we're going to keep it in meters. And you're at the back of the bus, and your goal is to walk at a constant velocity. Let's say you walk at 2 meters per second. Your goal is to walk from the back of the bus to the front of the bus. Okay? We can ask some easy math questions around, for example, how long is it going to take you walking at 2 meters per second to travel that distance of 14 meters? It's division, and we come up with 14 meters divided by 2 meters per second, and we come up with 7 seconds. Okay? Let's assume now that the bus is moving. So you're at the back of the bus. The bus is pulling away from the curb, but to make it simple, let's assume that its velocity is instantaneously at 1 kilometer per second. So if it's at 1 kilometer per second and you're moving at 2 kilometers per second, remember, your speed hasn't changed, but the bus is moving away from you. So the question is it going to take you longer than 7 seconds to get to the front of the bus, the same as 7 seconds or shorter? Longer, because you're on the street and the bus is pulling away from you. I probably left that part out. So you're not in the bus.
You got us on the bus.
Yes, I'm sorry, I put you guys on the bus. So let's try it again. So you're at the front of the bus and you're going to walk towards the tail light of the bus. Okay. Again, the bus is pulling away from you, driving in the forward direction like the driver would drive. Is it going to take you 7 seconds, more than or less than, before you hit the rear bumper? Less than, exactly. Okay. How about this one? What if the bus driver is instantaneously pulling away from you at 2 meters per second? Will you be able to get to the front of the bus?
Walking alongside it.
You'll walk right, basically parallel. You'll appear to be parallel with it. What if the bus is driving at 3 kilometers per second? Would you be able to get to the front of the bus? No. Right? So 2 or greater, you can't do what we've just asked you to do. We can in the opposite direction. If you're at the front and you're trying to get to the back, then he could go as fast as he wants, and eventually that back is going to get to you. So that direction, the reverse direction is fine. The forward direction, you run into trouble if the velocity of the bus, which we'll call victory lines, and we'll call our person on the street, we'll call her Carol, okay, for sake of conversation. So I have some specific times here that I'd like to share, but before I share that, I think I want to talk a little bit about averages, because this comes in, this is a pretty important concept. You'll see discussed throughout the book, and that is, I'm going to ask you to quickly come up with an answer, and I'm going to use my favorite numbers that I always like to use. And the question is, what is the average of 65 and 35? 65 and 35, and it will be the arithmetic mean for those of you who are more math inclined, but for everyone else it's your regular average. 35 and 65. Anyone venture the average?
50?
50. We have a chorus of 50s, and that is, in fact, the right answer. I would venture to say that most of you, perhaps not all, but most of you arrived at that answer by adding the two numbers together. So you have value A, 65, value B, 35, add them together, 100, divide by 2, 50. That's how most of us find the averages. It's pretty quick, it's pretty intuitive. What if you were asked to find the average without using the addition sign? Right? A little harder now. Still important, and for those of you who are in engineering or mathematics or computer science, you may have learned this technique. I know as a computer science undergrad, there's a concept called overflow, where if you have one number and you add it to another number, it may be bigger than what that memory chip or storage cell can actually store or hold. So you have to have other ways of doing your math so that you don't go what's called an overflow or go the other way, what's called an underflow. So in this case, what we do is we actually take the difference and we realize that the answer is going to be in the middle of that difference between the two numbers. So the difference between 65 and 35 is 30. And we divide that by 2, and we get 15. So I have a choice. I said let's not use the addition sign, so I'm going to take my big number and subtract 15 from it. So 65 minus 15 gives me the 50. Or I could do it the other way, if I didn't make that rule about not using the plus sign. I could take that 15 and add it to 35, and I still get the 50. So either one of those is a valid way of doing it. Let's go back to the bus example. So if we have Carol, I have to look at my math here. So if Carol is moving, and the bus length is 14 meters, Carol's moving at 2 meters per second. The velocity of this Victory bus is 1 meter per second. How long will it take her to go from the rear of the bus to the front of the bus? I won't ask you to do the math, but the answer is time is 14 seconds in this case. And the length she would have traveled is just that time times her velocity, or in this case, 28 meters. You could get the reflected answer, so how long from the front to the back, so the return trip, which is 4.66 repeating seconds. And then we can get the average, which in this case is 9.33. Now what's interesting is we know how to do the average, right? We could take the first number and the second number, and we could add them together and divide by 2. We can do that. But in this case, we can actually do the approach that I just mentioned, where you take what I call the half difference. So you take the difference and you divide that by 2, you take half of that. In this case, you take that half difference and it ends up being 4.66, and you either add that to the smaller number or subtract it from the bigger number. Let's talk about that though. Let's talk about these equations. On the back of the smaller card are some equations. I'm going to go to where it says number 3, so almost in the middle of the page. You'll see something that says A equals X prime over C minus V. And you'll see something else, B equals X prime over C plus B. For sake of our conversation right now, C stands for Carol, V stands for Victory bus lines. X prime is the length of the bus, 14. Okay? This is the equation that you would use to figure out how long it would take her to go to the front of the bus, or how long it would take her to come to the back of the bus. And up there you'll see I have something what I call tau sub A. That's how you find the average of those two values. The average, you could find it one way. You could go A plus B divided by 2. Or you could say A minus that half difference term, A minus B divided by 2. Either one of those will produce the same answer, which is just beneath that, which you see written as X prime over 1 minus V squared over C squared. Okay, well, let's not talk about that just, or excuse me, that's the length because I've multiplied it by c. So I've already jumped ahead one step. But let's go back, let's stay talking about time, a and b. So I said you need to subtract that half difference from the larger value. That's one of the ways I said, let's do it if we're not going to use addition. What's the half difference? Is there an equation for the half difference? Just the half difference. There is. If you go up to the top right-hand corner, you'll see something called Vx prime over c squared minus v squared. That's the half difference. And t, in this case, I'm not going to go into all of this in detail, but t, it's a function variable. For those who are comfortable with computer science, it will get replaced, so it can have a different value than t elsewhere in a system of equations. T, in Einstein's derivation, he replaces with a, which is x prime over c minus v. So if you do that subtraction of the half difference, you actually get this, you multiply it by c. This happens to be the average length. So what does this answer? It answers the question, in the case of the bus, what's the average length that Carol had to walk of one direction and the second direction? Okay, not the total length, not the length in one direction, not the length in the other direction. It's the average of those directions. It's her average length. Does that tell us the position of the bus? Does it tell us Carol's position? It has nothing to do with the position. Okay, that's very important. Now, why is this important? Why is it on here? Because these are the exact same equations. We've talked about it in non-relativistic terms because, again, prior to that period, I don't need to talk about relativity, but these are the equations that Einstein uses and develops prior to that period. So, where he says tau, and right now tau is an unknown function, and he doesn't really go into it a whole lot, what it does is it finds the average time. He multiplies that in his derivation by c, which gives you an average length. Okay? Now, why is that important? Because when you start talking about cyclical behavior, right, or wavelength, and many of the experiments we do are wavelength-based or frequency-based, right? We're actually talking about this scaling behavior. That's what our experiments are actually testing. They're not actually testing positional change behavior. Okay? So that's really important. So let's go back, because now this raises another obvious question. Steve, you're telling us that Einstein's equations are just the average. Come on, dude. We've been around debating Einstein for 100 years. You telling me no one else has never come up with this before? Actually, I'm sure it has, and I can show you where it has been. It's called the Michelson-Morley experiment. They actually use the average. Now, if you go back to the back of the bookmark, you'll see what I call the core scaling equations, or core scaling equation. I'm not going to go into that. I just want to go into the text that says classical mechanics, relativity theory, and modern mechanics. So let's just talk about classical mechanics. What Michelson and Morley do in their derivation is they just replace that x prime value with wavelength. Okay? And guess what? It didn't work. Okay? So, Steve, you just did all this work on averages and you're telling us it doesn't work? Okay, stay with me. So Einstein came along, and maybe some folks before Einstein, I'm not 100% sure, although I do have my own opinion. Einstein came along and he said, oh, you know what? That didn't work, folks, but I have something that works better. And what he did is he came up with a similar equation. He replaces x prime with wavelength, but he also does something else, which many people before me have highlighted, which is he drops a beta term. So from that equation that's on the other card, he actually drops a beta term. Now, it's hard to argue that he's dropping a beta term is a mistake, even though it is. It's hard to argue because it produces a better answer. And we're going to have to come back and explain why that is, which we'll do. Now, this becomes part of the problem that we have as anyone who's trying to challenge an established theory. So for the moment, just put your thumb over modern mechanics, and you see that there's two options. You have classical mechanics, which performs poorly, and you have relativity, which arguably performs better in many cases. Okay? Now, if any of us say, we want you to no longer believe in relativity, most people in their mind only have one alternative at the ready, and that's classical mechanics. And most people aren't willing to go back and just say, I want to go to classical mechanics, when we already showed that that doesn't work well for us. Okay? Actually, it does work well. But one of the things we had to do is realize on that picture, remember that cyclical behavior, right? Wavelength is a complete cycle. The equations expect half that length. It's the one-way segment length. So so modern mechanics actually puts that in there for x prime. So it uses lambda over 2. And when you use lambda over 2, you actually get a better result than even Einstein's equations. And you get a better result in both the Stilwell atomic clock experiment, and you get a better result in the Michelson-Morley experiment and Miller's repeat experiment. So both of those are pretty powerful. And we'll talk about that in just a moment. Let me just check time. Okay.
You have 2 hours.
Perfect, thank you. Okay. Okay. So one of the things that is pretty powerful is that if we have something that now people can come back to and say, okay, wait, let's talk about the math, Steve. So you're putting that math in there, you're putting lambda over 2. That's not going to give you the same thing that Michelson-Morley had. It's not going to give you the same thing that Einstein had. How are you telling me that this is going to perform better? Well, that's a great question. Well, what we've done is I've analyzed the equation against the Michelson-Morley data. Thankfully, they put the data in their paper. And what I found is that their data, when evaluated with this equation, I forget the exact number, but it returns roughly 32 kilometers per second, which is pretty close to the 30 or 29.7 kilometers per second that they were expecting. Okay, well that's great, Steve. So I'm glad you were able to do that. Maybe you just fudged the answer because you wanted to get that answer. Well, the nice thing is Miller, in his 1933 paper, also provided his data. And you're able to analyze that data using the same equation, and in that one you get the 30 kilometers per second as well. So you have 2 experiments that previously did not converge on the same answer. One gave you about 6 to 8, the other one gave you about 11 kilometers per second. Now, they both give you 30, so not only do they give you a desired result, they also experimentally converge, which gives us a higher level of confidence that we're on the right track. When we talk about Ives Stilwell is actually an interesting experiment, and I need to turn to the page so I can tell you the data there. So in the Ives Stilwell, they use what they call a relativistic Doppler equation. And in the relativistic Doppler equation, they might expect a result like 21.42 wavelength. I have to remember how big it was, but it's 21.42. And the expected result was 21.37. So they were off by 0.05. Which for all practical purposes is a really good answer. And it's far better than you'd get if you were looking at using the unadjusted classical mechanics equation. But once you use the modern mechanics equation that we just talked about, the expected result there is a 21.42. So you actually get 0 amount of error. So now that's to the limit of the data that's provided, and we will need to talk about degrees of significance, because that's one of the most important parts that happens in what I'll call the sloppy area of Einstein's work, and some of the early work is dropping significant digits and using them as if they were still truly equal, and that gets us into trouble. Now, again, different era, right? And you had to use different tools and techniques, but where we are today, we have different tools and techniques where we don't have to drop those things in terms of our analysis. There's a technique, so I want to go back to the question. Well, Steve, how is it that your equation and Einstein's equation gives similar results. We were under the impression that Einstein's equation is the only one that can answer some of these types of experiments. Well, thankfully, there's a technique out there for many of you who remember your calculus called a Taylor series. For those of you who don't remember calculus, I'll use an example. So pi, the number pi, for many of us, we learned at school is 3.14 and some other digits. And as a crutch, some of us learned that pi is 22/7, which is 3.14 and a bunch of digits. Okay? I would ask, are those two numbers equal? Is pi equal to 3.14? Now, most of us in the room who've done some math would argue, no, they're two different numbers. Pi is a very interesting and important irrational number, never ending, 22/7. By the time you get to the third significant digit, it starts to change. It's not the same. Well, a Taylor series works like this. You break it down into parts. So you say 3 plus 0.1 plus 0.04 plus, etc. And each time you get more and more and more what we'll call level of precision. Okay, and you do that for 22/7, you do that for pi. At a certain point, you say, oh, these are different. But up to a certain point, up to 3.14, they are the same. Okay. Why is that important? Because if you take the Taylor series of Einstein's equation, and you take this Taylor series of the modern mechanics equation, they both have the same first term. And what's interesting there is, in Einstein's work, when you look at his energy equation, for example, all he uses is the first term. So if all you look at is the first term, so to a certain degree of accuracy, you won't notice any difference between modern mechanics equations and Einstein's equations. We explain them completely differently, but you won't notice a mathematical difference. I like Ives Stilwell because they give enough accuracy that you can actually get more levels of significant digits to start to glean a hint that maybe there is a difference here that we need to explore further. Another nice thing is that the energy equation, which will be different, it gives you, again, what's interesting here is the Ives Stilwell equation is an application of Einstein's energy equation. And so it gives, using modern mechanics, we get slightly better answers. But if you look at the math and the derivation, which we won't go into tonight, but if you go through that and then you set the velocity to 0, it actually decomposes into the Newton energy equation. So you actually get kind of 2 for 1. So it's kind of cool. Okay, so those are kind of the key points that I wanted to talk about tonight. And what I want to kind of begin to wrap up on is a little bit about strategy, because I know that that there's a lot of different ideas out there, there's a lot of different thoughts, there's a lot of different ways to approach work and how we do things, and what I'm hoping is at a minimum, at a bare minimum, if there's nothing else that you want to take away from our discussion this evening, is this idea of PAW for a strategy, which is problem, alternative that ideally works better, and reasons why, the big W, right? If you have a pet dog or a cat, just look at their paw every now and again and remember paw. So if you take nothing away, if you don't want to agree with anything that I've said tonight, please take away paw in terms of your strategies, in terms of reaching out to people, whether they're dissidents or people in the mainstream. The second part is I do hope that there's elements of what we've walked through today that give you something to think about. Maybe you don't agree with what I have to share about modern mechanics. Maybe you have your own idea. And that's fine. Just keep in mind PAW, right? So you have to state the problem. It can be theoretical. It can be experimental. Alternative, ideally should perform better, because if it doesn't perform better, people will immediately say, well, what you have is an alternative interpretation, and it gives them an avenue for an easier dismissal. So ideally, you want something that performs better. And why? Because leadership requires us to go to where they are and bring them on the journey, right? And if all of us step over to the other side and can say, I understand why we've believed this for the past 100 years, okay? Doesn't mean we have to continue for the next 100 years, but let's at least examine why we believe that. Now let's walk over here together, right? The other way is you start over here and you say, come on, who are you? Right? The third way, which I've seen, and I think we're moving away from, and I think David framed it very, very nicely with the kind of vision of the organization, right? But the third way, historically, for some people have been to be on this side and say, what do you mean you don't see what I see? And start to throw stones. That won't bring people across the bridge with you. It won't take them on your journey, and it is not an effective form of leadership. Okay, so for us, as scientific leaders, our mission is to go to the other side, grab people by the hand and say, I understand what you believe, and walk them to where we'd like them to be. And I think that creates a very, very powerful punch. Now, one of the things that I've been asked, or one of the things I've heard is around, well, you know, Steve, we've been down this path before. The mainstream, they don't want to hear it. I've heard people say that earlier, right? If you say certain things, you're ostracized, you're asked to leave your position, there's other things bad things that can happen, and some of those effects are real. I'm not going to get up here and say that they're not real when people in this room have experienced it. But that's not everyone. And we don't have to change everyone's mind. There's a notion out there, and there's a book by Malcolm, I forget his name, I should have written it down. Anyone who's interested can find me afterwards. The book is called The Tipping Point. And the idea there is that in order to basically affect change, you don't have to convince everybody, you just need to affect a critical mass. And they've given a percentage to that. They said it's about 6 to 10%. So our goal is to change the minds of 6 to 10% of other scientific leaders and get to that tipping point so that the momentum really starts to fall into our favor. How do we do that? Remember the votes that we did earlier, right? If each of us can go talk to 4 people, and they can go talk to 4 people, and so forth, on just some of the key ideas that you might like that resonate with you, it only takes 4 generations, maybe a little bit more, 4 to 5 generations, depending on exactly the number, to get to that tipping point. So it doesn't take a ton. Now, some of you may say, well, Steve, you haven't addressed the point around this ostracization, this idea of people shunning us and asking us to leave our academic positions and things like that. And I can say that while that's real, recognize that there are folks out there who are accepting. Some of them have been in this room or in this room in previous sessions. I've had the pleasure of talking to people at 2 universities around the San Francisco Bay Area, both of my undergraduate school and my graduate school, and a couple of other universities where people have actively engaged, not just, there, Steve, thank you for coming, but really, okay, I'd like to read it, I'd like to engage in a debate, and let's talk about this. Things are changing. When I was at San Diego State, they are putting together an innovation center, which is really exciting because what they're trying to do is bring together a bunch of different disciplines. So they want to get the physicists and the engineers and the mathematicians and the business folks all in the same room so that you can have the synthesis of ideas in a way that hasn't happened before. And so in February, early March, I had the opportunity to go meet their VP of Research and the Dean of the College of Science, share a little bit about what I'm doing with my book, and also a little bit about what they're doing for the program. And it's really exciting in terms of what they're doing and their openness to talk to folks from the community about things that in the past we might have said, oh, I'm not going to approach them, they're mainstream. So I just want to let people know that the experiences that we have, that there's going to be some folks who are going to see you coming, they're going to close the door. That's the reality. But there's also going to be folks who are going to want to understand what is it that we have to say and how might we want to say it. So I'm going to leave you with a couple of thoughts. And this one is also from my daughter. Actually, it's not from her directly. It's actually from Isaac Newton. But it's from a book that my daughter gave me as a gift. And the book is called Newton and the Counterfeiter. And I just finished it. It's an enjoyable book if anyone's interested in Isaac Newton, his life, his discoveries, his later life when he worked kind of for the English Mint, and it's a very fascinating book. But in there is a quote from his book, his optics book, and it says, "To explain nature is too difficult a task for any one man or even any one age. It is better to do a little with certainty and leave the rest for others." So I leave you with this thought. I hope that what I've shared today is a beginning. I hope it is something that is simple and something that we might be able to say, okay, let's have a debate, let's have a dialogue. Maybe we're not ready to agree with you yet, Steve, but it's the promise of there's so much here and there's so much for us all to do. It's that promise that excites me, and I hope is something that excites you. I hope that you've heard something that you've liked today, and if not, then I hope that you'll give me a chance to meet you later in the week and change your mind. So, but hopefully you had a good time. And if you like what you've heard, definitely feel free to check out my material. I do have a couple of books up here if anyone is interested. You can follow my blog, stephenbbryant.com. And I think those are the main things I want to say. So I wish you all a great success in the rest of our conference this week, and a wonderful evening, and thank you for your time.
Okay, questions, comments, discussion. Let's open.
Okay, so we'll open it up for Q&A for anyone who might have any, or we can just, I know it's kind of late too, so if people wanted to pack up and go for the evening, then that's okay too. Duncan.
Okay, Steve, I've been listening to your treatment of the mathematics underlying your modern mechanics. But I've also been listening for a word picture of modern mechanics. I don't think you covered that all, but if it's to be convincing and underlie, as you're hoping, a general agreement in this society, don't you need a physical picture of what your modern mechanics creates? Do you have?
So the question is, do I have a picture that describes modern mechanics?
Yeah.
And what I have, Duncan, is on the back of the bookmark under the alternative is a picture that I think captures the key elements. It doesn't have the math that's associated with it there, but that's it has partial. So the model consists of three parts, right? An inner system, an outer system, and an oscillating system. And it's that recognition of an oscillating system as its own system that distinguishes it from both Newton's work and Einstein's work. Both systems can be described in terms of a translation equation or a scaling equation. So in the case of the inner or moving system, what we have emphasized is the translation equation, which is commonly referred to as the Newtonian transformation, x prime equals x plus vt. If you are interested in that oscillation behavior, which is the scaling behavior, the stretching of the rubber band, then that's governed by a slightly different equation, and that's the first part, the b squared or beta squared x prime part on the back of the card. I have minus x there because in use, the equation is used in terms of a relative term. So you have your original, let's say, frequency or wavelength, and you subtract that off or merge it or something with what is reflected back or what is observed.
Okay, that expression, oscillating system, helps. What is it that's oscillating? Is it something conceptual or something physical? What is it?
So in the case of the example that I gave, it was Carol, right? So she was going back and forth between the front and the back of the bus. In the case of Einstein's work, and I don't have that page up in my iPad, or I can show it to you later. It's his ray of light. So if you look at his, there's three function invocations that he does. So first he says, tau 1 plus tau 2 divided by 2 equals tau 0, something like that. Anyway, he gives some math. But what's oscillating when you look at the equations and his text is he has the ray of light going in one direction, and then he has the ray of light coming in the other direction, and that's how he arrives at the same equations that I showed earlier.
What's a ray of light? What is it physically?
So I'll be honest, I don't know the answer to that. I will say that one of the things I'm excited by in terms of light is some of the research that's happening up in MIT, and I forget if it's their computer lab or their photo lab, but I can find that out. But they're doing some stuff with super slow motion, and it's really fascinating because they take a light and they fire it off, and they might have like a can here and then a wall here, and the way that they do this, they image capture, and you actually see that wave of light moving in slow motion, hitting the wall. Someone talked about scattering earlier. You see it scattering. It's really fascinating work. I can find that URL and send that out if anyone's interested. And again, that's work coming out of MIT. Go ahead.
Yes. Could politics, international politics for that matter, play any role for or against any organization like this one? In any organization like this one, which is engaged, which might be engaged in rewriting the laws of physics.
So the question is, could international politics or different organizations play a role either for or against some of the messages and I'll call it mission and vision of an organization like this? So as I mentioned earlier, I spent a lot of times in business. And I can say that and just like many people, you don't have to be in business, it happens everywhere. There's always politics at play, whether it's politics of your team, of your group, of your division, of your organization versus some other organization, regulators, partners, competitors. There's all sorts of things that can go for or against. I think that where could it go against? It can go against with people who, like, if, for example, if Dr. Tyson is not at all open to even having a conversation around an alternative, then he might be part of an organization that might not look at what we're doing too favorably, right? So that could go against. This organization has partnered in the past with other groups. When I first joined, I know we were still doing some meetings with the American Association for the Advancement of Science, AAAS. And I've had a chance to actually be a judge in some of their competitions when they were out in San Francisco. I delivered a paper out there and judged some student presentations. And they were accepting and open of what I had to say and share. So I think the answer is it's going to depend, but it will also depend on us. If we're out there and we haven't yet figured out what our message is, if it's an individual message, it's much easier to discredit than if it's a group message. And if it's a group message, then it has to be something that has been vetted, right? This has to be vetted by this group, and people have to kick the tires and say, Steve, we've kicked the tires. We think you're wrong here, and I should have a chance to respond. So Steve, we've kicked the tires, and we think you're right here, and then other people will have a chance to respond. So it has to go through that process before we can have it fully accepted.
I was interested in your talk, in your book. The approach that I gave in the presentation this morning, I don't know if you were here for that or not, I was using the argument that logic, relativity theory does not pass the logic test. It can't be combined with other theories because it's not linear theory. It involves C, and so do many other theories, including electrodynamics, so it can't be a fundamental theory. Only true theories are fundamental. Only fundamental theories are true. And then I showed from how you doing a more complete version of electrodynamics that you were able to explain all the results in electrodynamics, at least, from special relativity without special relativity. So the principle of simplicity says, which is better, one theory or two theories, or more? You know, and the answer is supposed to be simplicity. If you have one theory that explains everything, you should use it, not a whole bunch of theories which are incompatible with one another, logic. So that was the kinds of arguments that I was using, and it doesn't require any predictions from data that are different particularly. In other words, even both theories might predict exactly the same results in electrodynamics, but you know from logic and you know from simplicity that special relativity is not needed. So if you throw it out as unnecessary baggage.
So the comment was a reference to Charles's earlier presentation and some of the arguments that he made about how one might go about using some of the I'll call it axioms and some of the, I forget the exact word, but some of the earlier arguments.
Theorems of meta theory.
So theorems of meta theory. Thank you. So a couple of comments. First, so thank you for your comment. I was introduced to your work a few hours ago, so I haven't had a chance to completely digest it and understand how it might reflect on what I'm sharing. One of the things I will say, though, is that part of the power of the spherical wave proof analysis is that because we are able to challenge Einstein's work before relativity comes into existence, we can apply the rules of mathematics, which means we take it out of the hands of only physicists being able to have the conversation, right? So now physicists need to be involved, but mathematicians can be involved, engineers can be involved, computer science people can be involved, other people can be involved, because we're no longer talking about post-proof and all the other terms and concepts that go along with it.
Well, another comment I had was, for the same year that Einstein put out special relativity, he also, his wife published, and he put his name on it, the paper on the photoelectric effect. And the conclusion of that paper was that light was a photon, which is a particle, and not necessarily a wave. And so the equations that Einstein wrote for special relativity are not wave equations, they're particle equations. And you seem to be interpreting them as wave equations.
So the comment is Einstein's work was later discussed as, I'm going to just summarize it. Basically, it comes back to, is light a wave or is light a particle? And I will say that I address both in the book. Today I did not go into that level of detail, but both have to be addressed if we want it to be able to explain some of the observations in quantum mechanics, like the double slit experiment, so which is actually a very, very fascinating and fun experiment in its own right. Okay, additional questions?
Yeah, I want to follow up on this question about does your theory relate to a realistic, visualizable thing?
Mm-hmm.
And let me give the following example. The second postulate says that observations are of special relativity. The second one says observations are subject to the observer. The speed of light is constant relative to the observer. That's our second assumption?
Mm-hmm. Mm-hmm.
Okay. So here's an example of a situation that is constant for the observer, or the observer sees it. And that is, you have a water fountain, and there's people standing in front of it, and you walk around, and you describe what you see. So I look at the fountain, I see this, and there's a person standing in front of it, and the water's coming, the sunlight's a certain way. So Charlie walks around, he's about 5 feet to my right, he looks, he says, well, yeah, I see the fountain and I see a person, but they're not between me and the fountain, they're off to the left. So he sees a different thing. And then the third person walks over and they say, here. So each of the observers has a different view that to them becomes their reality, their frame, right? However, in this situation, no matter how many people see a different thing, somebody can resolve it back to a single thing. Okay. Einstein, you can't do that, right? So Einstein stuck with this problem he's got the twin brother paradox. But there's another paradox that's even different, and it's called the light transition paradox, which means 1 billion years ago, a light beam starts off on a star somewhere, and it's heading toward us. And it has to pass another star, it has to pass these planets, and so forth. And that light beam could track a certain time sequence coming here, which doesn't depend on any of us seeing it. Yet when we observers look at it, according to Einstein's equations, we're supposed to assume that our theory, our vision of reality is true. But it doesn't match any of the transit. It's different from the transit experience. Instead of saying that, no, there is an absolute transit. This light came and it clipped along these certain things at a certain time in its own frame, in the light's own frame. And we all ought to be able to resolve our view of it back to this true, this standard model. So I'm wondering, does yours even address one of those or the other, the twin paradox, and resolve it? Or is it still stuck in it's an unresolved paradox?
So thank you, Bruce. The question is, I'm going to paraphrase the question. Does my model have either the same or similar paradoxes as Einstein's, and how do I resolve them?
Sure.
So because I am explaining something different than Einstein, and I come up with different equations, I don't use those same two postulates that he does, which means I don't arrive at a place where I have a couple of things. I don't have paradoxes, nor do I have the constraint. I have conditions, and there's a very important condition, but and we can experience the condition today using the equations on a different phenomenon. So one of the nice things about the equation, right? We developed these equations that we walk through tonight here using Carroll and Victory bus lines, S, C, and V, right? So just that's what they are. And then I asked you to take a leap of faith with me and say, look, these are the same as Einstein's equations. And they are a leap of faith until you go and look at it for yourself. Section 3 of Einstein's 1905 paper. But here's the other leap of faith, which is, actually this one's, again, you can verify for yourself as well. These equations will also apply to other phenomena like sound, right? So what happens if, and we had a big debate, I forget what year it was, I want to say it was in the 30s, but I should have done the research before I got here. But we did have a big debate, either in the 30s or 40s, I forget the exact year, maybe even later, but I thought it was the 30s or 40s, as to whether or not mankind, humankind, would ever break the sound barrier, right? Many of you may have read about that debate, and that is a very important one because theoretically, it was similar math, right? Something bad happens, right? The math breaks down when your velocity hit the speed of sound. And in fact, at a certain point, it became an engineering challenge and a physicist challenge, but an engineering challenge because in order to break through it, we had to do a lot of design changes to our aircraft and our vehicles, otherwise they disintegrated, right? So part of what we found is that sometimes the math only works to a point, right? So this equation that's on the back that I said was the average length for Carroll, well, the average length is the combination of two things. It's the average of the forward distance, oops, if the bus is going faster than Carroll, she'll never get there, and the reflected distance, which she can always do. Well, the average is both of those, so how can the average have any sense if she can never get to the forward part of that, right? So at some point, when velocity of the bus equals velocity of Carroll, you get 0 in the denominator. It's undefined. Well, what does that undefined mean? Well, when you're talking to relativists, it means a certain thing. For my model, it just means the math doesn't explain it anymore, just like the math doesn't explain what's happening to the sound wave when the vehicle is exceeding the speed of sound. There's different math that applies.
Right. So you answered my point very well. If you don't have the paradoxes coming up, which were major challenges to his theory, then you can add a double best, a double improvement to your statement here, saying your new approach resolves the paradoxes that he couldn't relativity theory can't get around. That's an improvement to the theory.
That's a great point, Bruce. And I think for the next iteration of the card, I'll make that in there. So for those who didn't hear the comment, Bruce's comment was the fact that this model doesn't have the paradoxes that are associated with Einstein's theory is an additional benefit. It's one that we want to make sure we articulate and communicate.
Right,
Thank you
yeah.
for that. Okay. Here and then there and okay.
Yes. Would I be correct to say that physics is lost in the bush? And it has to do a lot of beating about the bush before it could find its way out of the woods.
So the question is physics lost today? Right? Is that a good way of paraphrasing it?
Yes.
Okay. I will say that the purpose of many of what we do in physics or mathematics or computer science, which is the domain that I have spent a lot of time in, is you come up with useful models and you continue to use those models until they're no longer useful. So something breaks them, they collapse, something comes along and you go, oops, or until you come up with something better. If we collectively review this work and we agree, this is better, and we share that message and physicists say, the mainstream says, we're not going to listen to you, etc. At that point, I would say that they're lost, because if they're not willing to examine something that produces quantitatively better results, then that is not the role that we want to play in mathematics, engineering, or science. Are we lost right now? It's a useful theory. It provides good answers in many cases. Does it always work? No. Do I believe it's right? No. But as I've shown with Ive Stilwell and others, there are plenty of cases where it does provide useful results. So the question is, again, if you put your thumb over the line that says modern mechanics, if our only choice is classical mechanics or relativity, relativity at that point is the best game in town. We need to use it. If, whether it's modern mechanics or some other model, comes along and provides better quantitative results, which means they're just mathematically superior, that's the point where we have to examine that model. And if people don't want to examine it, and it is quantitatively better, that's where I would argue that we're lost. I don't think we're at that point yet, but hopefully if we get that multiple that we said, 4, 4, 4, we'll arrive at that point pretty soon.
Yeah. Special relativity and general relativity also have a number of assumptions that are built into the equations. There's the assumption that the universe is homogeneous and isotropic, but we know, looking out at the universe, it is not homogeneous and isotropic. And just our solar system, you can just see it's not homogeneous and isotropic. And another one is Einstein's equations involve the point-particle assumption or idealization. And all the particles that we know of in nature have a finite size, and no finite size effects are included in special relativity. And so, do we falsify theories by there being incorporating known false assumptions, which Einstein's special theory of relativity has 5 known assumptions that are false. And right now, the role of logic in science has been removed, and no theories are falsified because the ideas they're built upon are known to be false.
So the question is, can we falsify a theory based on a flawed assumption alone, right? That's a good way of paraphrasing. I would argue that if we can find the right argument, then the answer is yes, right? In fact, I would say that that's what I'm doing, because if you look at Einstein's spherical wave proof, right? The power of that is, I'm not saying, look at me, I've come up with this new proof to prove Einstein wrong, right? There's no power in that, because you're going to go, who's this Steve Bryant guy? The power is, Einstein tells us, I don't have it yet. I need to prove it. And until I've proved it, there's no such thing as relativity. So he tells us, I have these two assumptions, these two postulates.
He has more than that.
Well, the two that he's trying to prove in that case, so that there can be others, but the two in this particular case, and what we've done is we've shown that there's actually 5 steps that Einstein performs in that proof, in terms of starting with a sphere, showing the equation, showing the transformation, getting a new set of converted points, and then concluding that they're a spherical wave, by using the equality sign alone. So left side of the equation, right side of the equation equal. If you do that, you'll reach the same conclusion, and it's going to be hard to say that those two assumptions are wrong. But if you go back to, again, not Steve Bryant introducing anything new, but going back to what we all know, what's the definition of a sphere? Has to have a constant radius. Does it? We examine that, it doesn't. Now we're able to use Einstein's own words and say, okay, these two assumptions that you said were compatible aren't, and therefore anything that happens after this period falls out. You have not shown relativity is valid. So I'm not proving it wrong, I'm showing he never proved it right. And there's power in that. Now, to your point of assumptions, there can be other assumptions. He makes assumptions in general relativity and that special relativity is right but incomplete, etc. Well, if he's made that assumption that special relativity is right, and we've just shown that it's not, it calls that into question.
For 2,500 years, Einstein's theory of relativity would have never been admissible as science because it was based on known false assumptions, and no theories were allowed in science based on known false assumptions. Only in the last 100 or so years have we allowed theories in science with known false assumptions.
Okay, so the comment.
How do we change that back to the way it used to be?
So the question or the statement is, how do we change things back to what we'll call a disciplined scientific approach for things?
Classical.
So one of the things I found interesting, because you said for a long time something like Einstein's theory of relativity wouldn't have been accepted. What's interesting is, had Michelson and Morley used wavelength over 2 in their equations, we might not be having a discussion about Einstein today. Using their data, we might not be having a conversation about Einstein today.
Einstein denied that he was influenced by that, though, too, didn't he?
That's correct.
I'm not saying that I agree with you, but that's a whole nother thing. It's because if what your assumption makes sense, but he says, well, I didn't even know about that.
Right. So David's comment is, does Einstein really explicitly reference or talk about Michelson-Morley? And in his 1905 paper, he does not. There's very little in the way of references in that paper. So the debate is, from other researchers of the time, which may have similar equations. Did one of them copy from another? Did he get his wife to help? All that I don't know the answer to. I have my own speculation, and I'm not going to go down a speculation path. Not while I'm being recorded, at least. But one of the things I will say is that that doesn't matter for us, because if we can stay focused on a message which is, look, as a starting point, as that foundational piece, that rebar, that cement for our foundation, if we can agree that, and again, it will require vetting, right? You can't just take my word for it, but if we can agree that that transformed shape is not a sphere, a spherical wave, that can become a foundation upon which we can all build, and it's something that someone needs to respond to. And when they say, well, it gives good answers, well, we have something that gives a little bit better, and we can explain why it gives the answer that it does. It gives us a powerful platform from which to engage in a conversation. It doesn't mean that this is right? It has to be vetted, I recognize that. But I do think that there's something that is worth exploring, and if it is vetted and we agree, that it can become a powerful foundation upon which we can build.
Yeah, I think you make a good point there. There's a difference between coming up with a wrong conclusion that I'm going to call this secondary wave a spherical wave when it's not, as opposed to a simplifying assumption, which is I'm going to take a point particle when Bill's saying there's no such thing as a point particle. I can do the whole celestial mechanics, making all the planets as points, and I know they're not points, but it's a simplifying assumption to do the math,
Math is easier, yeah.
and that works a lot of times, so.
All right. But-
Okay.
but let me.
Let me go to the back and then back up to you.
Just because my memory's a little poor, are you saying, you discussed 3 different experiments, one, the Michelson-Morley, and then the last one was the Ives and Stilwell. I don't understand completely is, are you saying basically that the Michelson-Morley experiment did not entirely end on the null, and that your equations, your what you propose hits that better? Are you saying that your equations hit the null exactly, and that Michelson-Morley's experiment hit the null? Let me just start with that question. I don't. Okay, fire away.
Okay, so the question is, how does my work align with the Michelson-Morley answers? Is that the correct way of capturing it?
Yes.
Results. Okay, so here's an interesting way of thinking about it, and I'd ask this question for anyone who has studied that experiment, and that is simply this: throw out an expected result. Throw out 30 kilometers per second, throw out 0. You have neither. Okay? You just look at their experimental data, and you're asked to play the role of a data analyst. And your role is to simply come back with the answer, what velocity does the data tell us that the Earth is traveling at? Okay. If you do that, then you'll come up with 2 very important numbers. You'll come up with a mean, an average, you'll come up with a mean, and you'll come up with a standard deviation. And you can use statistics against the mean and the standard deviation. I forget what it is, but if you go out, I think it's 3 standard deviations, you get 97%, or is it 99.7? In either case, you get a big number of where your expected results are supposed to be. And you can put a normal curve on that. You can say, with 90, call it 97 or 99.7% confidence that we believe that the Earth's velocity as it goes around the sun is between number A and number B. That's how you'd answer that as a data analyst. I'm almost certain, 99% certain, that it's between A and B. That's how you'd answer it as a data analyst. You don't say, because I didn't get 30, I go to 0, right? Here's the thing, A is about 6 kilometers per second, and B is about, is it 8? I'd have to look it up. I think it's 8 kilometers per second. So anything that's less than 6, so let me rephrase that. If it's between, we are 99% confident that the Earth's velocity is between 6 and 10 kilometers per second, using their data, using their experiment, which means what? It means 30 isn't a valid answer. We're not 99.7% sure, but neither is 0. So the absence of one answer does not automatically mean that the other alternative is the right answer. So 0 is not an answer. So we have to find something else. And what I found is, again, when you use these equations, which use the segment length, half a wavelength versus the full wavelength, and there's a whole section devoted to Michelson-Morley, both in chapter 1 and in chapter 7, where I walk through it in detail. You walk through and you get the answer that's about 30 kilometers per second. And again, the next question is, Steve, well, that's a fudge factor. You decided you'd come up with something that was 30. And this is where you go to the Miller experiment, and he came up with about 11 kilometers per second, so a little bit of distance between him and the original experiment. you use his data using the same updated equation, and you get like 29 point whatever. So they both converge around 30. And the fact that we get something that now aligns with a theory, not necessarily mine, but a theory, and you get two different experiments done at different times that give similar answers, that gives us experimental convergence, which gives us some amount of confidence that we might be looking at something through the right lens. Again, that's something that would need to be vetted, right? So it needs to be, the tires need to be kicked on it, and it needs to be explored further.
Yes, the question I was going to follow up on Charlie's point is, you know, if you're doing the calculations of the planets around the sun and you use a point assumption for gravity, it's a very different thing if we apply that toward a black hole. Because if you look at what Kawasaki says when he keeps talking about his equations and Stephen Hawking's about his equations, what do they think the gravity level is at the center of the black hole?
So your question's
Right.
around the gravity level at the center of a black hole, and building on Charles' comment about particles, and I will be one of the first to use the phrase "I don't know."
Well, yeah, but, no, I wasn't finished, because I'm saying, if you use 1/r squared, then you have an infinity there. You've got a, you've got a, what do you call it, isotope to infinity there, or so it's an absolute. But if you use Einstein's shell theorem, it's zero. And somebody ought to be able to come up and figure out whether the center of a black hole, the gravity level is zero or infinity. And
So,
it makes a big difference in what all the other things you're going to think about a black hole in the process.
So what you're saying there, Bruce, I think is a really good point for me to repeat if I can find it, which I can't find fast enough.
Singularity.
But basically,
singularity.
If this is a starting, no matter what, it's a starting point of a conversation. We're having a great dialogue today. And as I mentioned, I'm not going to be afraid to say, I don't know, when I don't know the answer to something. But that's just another example of the foundation upon which we can build. We heard a conversation earlier today, I forget who it was, and one of the comments was basically questioning, do black holes even exist? I don't know, but we can explore that. Now we can explore it using another model that may help us come up maybe with the same answer. Maybe it gives us an answer that's completely different. I don't know, but that's the part that excites me, is because we are at the door. We're about to open the door and cross the threshold of a scientific journey that I'm really excited to be a part of. And it's that belief of where we are today that I think is the promise of tomorrow. Because if we can agree on certain things, again, kick the tires on this. Maybe it's this, maybe there's a tweak, maybe it's some other theory. I don't know, but at least we can have a conversation, and even if it's just that we begin with. But I hope we at least take the problem statement with us as well. I think that changes the game, because it allows us to have a conversation about science, and we, in effect, neutralize the conversation about relativity by showing that we have our discussion, we have our argument, our analysis before relativity exists. So, and that's powerful, because I've had this conversation with a lot of people, and they'll say, well, what about time dilation and simultaneity? If you think about that, then this equation, sorry, Einstein just said that it needed to be proven, and it's not, so you can't use those terms yet.
Right. And
So I think that's the
solve it
promise.
without the terms. You see, that's important. No time dilation stuff.
Exactly. And then
Well, that's powerful stuff in addition to your other discovery of the paradoxes, right?
And let me take a cue from my director there, David.
running
How
out
much
of
more
film.
time? do
I think
have?
we can wrap it up, yeah.
Yeah, okay. So on that note, then, I want to thank you all for staying with us. I know it's been a long day for many of us today, but this is, for me, has been a phenomenal time. It's my first book talk, and so I want to thank you for making it a pleasurable one and an enjoyable one. So thank you, everyone, and have a good night, good evening.